Morning, everyone. Thank you for joining us today, Tuesday, for our KITP's Fundamentals of Gaseous Halos. Let's see. Okay. As we began yesterday, this week focuses on how does gas flow out of galaxies. It is our 5th week, so we just made it past the halfway mark of the program. Hopefully people aren't all burned out and are still excited for CGM science. I know I am. We had a wonderful event last night, a social event. Some of you I know were able to attend. It was Astronomy on Tap, featuring some related public level talks by Jess Work and Zach Hafen last night at 7:30 p.m. Pacific. And then we had pub trivia afterwards. Hopefully some of you were able to join and have fun. We will have more social events in the coming weeks. Next week, I believe we're going to do, it's not using town.gather, but it's something similar. It's kind of a cross between that and Zoom. It's called Room, R-U-M-E, and it allows you to join a Zoom teleconference kind of thing and then have rooms, but you can see who's in the rooms, like see what's going on, but you don't necessarily hear the sound. So it's experimental, but we'll do it as kind of a beer hour next week. I think we were talking about next Wednesday at 5 p.m. Pacific, but there will be more details on that. And then we're going to definitely do another trivia because that was so successful last week. So stay tuned. Today, we will be joined by our first keynote speaker of the week, Dr. Dylan Nelson, and he'll start in a couple of minutes and go until the hour. We'll have a short break, 5 minutes or so, before we have a panel consisting of Rongman Bordaloy, John Chisholm, Ramil Dave, Changu Kim, and Miao Li, as well as Dylan, discussing and addressing questions that are brought up by you during the keynote, as well as kind of organic questions that arise on the topic of galactic outflows. I know there's a strong preference by people to respond in the Zoom chat, but that doesn't really get preserved long term. So if I could ask people to have their questions, comments, and discussion in the Slack channel, Halo 21 Week 5 Outflows, that'll be better preserved, and it allows threading. So if somebody has a question, then someone can respond as a thread on that, and it keeps it a little bit more organized and sorted. So please use that Slack channel, and we can have discussions. And I'll be drawing from the discussions there and the comments there to seed the discussion for the panel after Dylan's talk. One quick note: you can use little emojis on individual questions that you think are really relevant, or kind of upvote them with like a plus or a thumbs up or something like that, which will also indicate to other members of the program, like you think this is important. And if you see a lot of pluses on something, then that might indicate that people should check it out or upvote it in that capacity. You could even give thumbs down. I saw a few thumbs down, so that's an option if you think it's a really dumb question or comment. Okay, so our first speaker for this week's theme of how does gas flow out of galaxies is Dr. Dylan Nelson. Dylan we finished his PhD at Harvard 5 years ago and has been at Max Planck in Garching for the last 5 years, and he just began last fall as a group leader at the Institute for Theoretical Astrophysics at Heidelberg University. He's really a young star in the field and has done an enormous amount of work in the last 5-10 years. He was co-PI of the illustrious TNG simulations and has done an enormous amount of work on the CGM, both small scales as well as highly ionized oxygen, a variety of different studies of the CGM, and we're happy to have him joining. I'm happy to have him joining. So do you want to share your screen, Dylan?
Yeah, thanks, Cameron. I will take over. I hope you can see that.
Yes.
And also that.
Yes, that looks great.
pointer. Very cool. So I hope everyone can hear me okay. If I drop out a bit, please just let me know and I'll kill my video perhaps. So yeah, thanks very much, Cameron, for the kind introduction. I'm very happy to take us into week 5. And the topic, the question I've been assigned here is how does gas flow out of galaxies, galactic outflows, the theory half. So we'll get the observational perspective from Tim Heckman on Thursday. And the question then, so how does gas flow out of galaxies? And I want to kill the suspense from the beginning, just give you the answer. And I think the answer is yes, right? We all agree. Yes, it does. Yes, they do make outflows and in spectacular ways. So although I've been told not to talk about observations whatsoever, I'm going to disobey that rule and give a very quick introduction to set the stage for this week in talking about outflows. In particular, how do we actually see outflows in the real universe? There's a variety of techniques, right? Direct imaging, especially in the local universe, in a mission where we're typically thinking about broad narrow line decomposition with the broad component representing the outflowing material. And also in absorption, so down the barrel studies where gas is blue shifted, representing gas flowing towards the observer. And more recently, perhaps also direct imaging, but molecular gas, CO. This is a redshift 6 example from ALMA. I would also group, say, Lyman alpha halos into this category. So a diversity of techniques for studying and characterizing the physical properties of outflows. And these data give us a very nice perspective on how outflows work and what their properties are in terms of the galaxy population. And I just want to flash through a few results which give a sense of that, the kinds of inferences that we can draw, right? How outflow properties relate to galaxies. So the first here is from Chisholm, 2015. It's a velocity of outflowing material as a function of galaxy stellar mass. This is a cold tracer, silicon-2, at redshift 0. Velocity is increasing for more massive galaxies, very broadly speaking. Similarly, outflow velocity again is a function of stellar mass, and even colder sodium D tracer, also redshift 0. Again, slight trends of increasing velocity with galaxy mass. So redshift 1, magnesium 2, again, outflow velocity versus stellar mass, increasing roughly, but lots of diversity, lots of scatter. On the right, I'm showing actually the mass outflow rate, so solar masses per year of the outflow, again, as a function of galaxy stellar mass. This time color-coded by black hole luminosity, so presumably tracing something here, the connection between mass getting thrown out of galaxies and what the black hole at the center is doing. Redshift 2, so this color is showing the fraction of galaxies with a strong detected outflow, in a sense, again, as a function of galaxy stellar mass. And here the y-axis is actually offset from the star-forming main sequence. So galaxies at the fixed mass, so going in a vertical line here, which have higher star formation rates, also tend to be more frequently detected with strong outflows. So there's clearly star formation rate outflow connections. And finally, something different, so strength of cold gas, magnesium 2 equivalent width, as a function of distance from galaxies. This is from Sloan, magnesium 2, and the green and the purple points are showing, respectively, sight lines oriented along the minor versus the major axis of galaxies, showing a preferential enhancement of cold, presumably outflow tracing gas along certain directions with respect to the galaxies themselves. So this is just to kind of give a taste of the kinds of data and inferences we can draw in the observational space, and which is to say that we have a very diverse and complex set of empirical constraints on galactic outflows. The question then is really, how do galaxies not get their gas, which is another favorite topic of mine, but how do they get rid of their gas? And if you'll indulge me, I want to schematically orient and set the stage here, just so we're all in the same, thinking about the same regime. And so we're sitting inside a dark matter halo. There's a galaxy, a disk galaxy at the center. Of course, we have inflows. We have cosmic gas accretion from larger scales. And in a sufficiently massive halo, this will form into a quasi-static hot atmosphere, right, with an associated virial shock. This hot gas can cool in a uniform fashion. And as we've also heard a lot about lately, we can also have localized cooling phenomena, in situ kind of cooling phenomena. Galaxies don't live in isolation, right? There are also other galaxies and galaxy-galaxy interactions and mergers. Satellite galaxy moving the other way will be undergoing stripping processes. And then, of course, galaxies are driving outflows. Outflows and winds, I'll use the two terms interchangeably. And let's not forget that not only central galaxies in the universe do such processes, also all the neighboring galaxies also may be driving their own respective outflows. Some of these may escape the halo, others of course don't, and they form fountain or recycling flows, and collectively, the buzzword here, of course, is the cosmic baryon cycle, all of this complex physics taking place inside the CGM and gaseous halos, which is why we love to study this topic so much. And today I'm really focused on just one element of this baryon cycle, which is the outflows themselves driven from galaxies across time. And so in this context, I see really three very broad questions, right? One is about the small scale launching physics. How do supernovae and black holes actually produce outflows? Second is what are the properties of those outflows as they propagate away from galaxies as a function of the galaxy types, galaxy properties themselves. So that is to say, what is the connection between outflows and the galaxy population? And three is what do outflows actually do to shape the galaxies, which is a topic for the future weeks of this conference. And so today I'm really going to be focused on the second question, which is what are the properties, the physical properties of outflows, and how do they relate to galaxies? And in this sense, I'm going to propose here that a fundamental quantity we want to think about is the mass outflow rate. So m dot out in terms of the solar masses per year as a unit. Now this has, of course, many dependencies. I think we can all agree that the amount of mass flowing away from a galaxy depends on the spatial location, so where you are with respect to the galaxy. I think we also agree that gas flows in different directions and with different speeds, so the outflow rate depends on velocity. And then, generally speaking, on phase, which I write here as temperature, density, and metallicity of the gas. And so if you allow me, I'll simplify velocity just to a scalar, so radial velocity, and I'll simplify the position into just distance from the galaxy and angle, some galactocentric angle with respect to the galaxy. And so what we really want to measure and understand then is the rate, how much mass and how much energy is flowing away from galaxies. How does this evolve with radius? What is the geometry of these flows? How fast are these flows? What is the phase structure in terms of density, in terms of temperature? And are these flows smooth or are they clumpy? What is their substructure? And finally, what is their metal content? And here, of course, I've omitted many other things also carried by outflows, which I won't unfortunately have time to talk about today. For instance, dusts, magnetic fields, and cosmic ray components also outflowing in the gas. Okay, but this is great. This is in some sense a very high dimensional function that we would like to characterize from the simulations and also empirically. But unfortunately, this is only half the story. It's only half of the dependencies here because the outflow rate from galaxies also depends upon the galaxy itself. I think we also would all agree. So even if we measure all these properties and how gas is flowing, that answer depends also on the galaxy mass itself. Say the stellar mass of the galaxy. And at fixed mass, it also depends plausibly on time, on cosmic epoch, on redshift. And at fixed mass and fixed redshift, it also depends upon, say, star formation rate. I think we also all would agree, m dot star related to the number of supernovae type 2 going off. Okay, I think we're on the same page for now. Maybe I start to raise some eyebrows when I say the outflows also depend critically on the rate of energy injection from supermassive black holes. And indeed, as I'll come back to later in this talk, the interplay between these two terms is crucial, indeed. But what else? So other properties of galaxies that outflows depend on. Here, I just give one example, kappa gas. So by kappa, I mean the circularity parameter. I mean a measure of the amount of rotational support of a galaxy, which is to say, is it disky? Or how disky or not disky is it in the gaseous component? Maybe it's not something a lot of us think about. How can the morphology of the gas of the disk actually influence and regulate the properties of outflows, say the amount of outflowing mass as a function of the temperature or the velocity? But it can. We'll come back to that later. So the questions that we're asking here on the bottom half of these dependencies are really, how do outflows evolve with mass, galaxy or halo mass, with redshift, and how are they set by the available energetics from supernovae and by supermassive black holes, and what is the interplay between those two processes? And finally, other galactic properties such as morphology, which can actually be quite relevant for galactic outflows. Okay, so from my perspective, this is a computational problem, right? I'm giving the theory perspective, and we would like to understand outflows, which is to say feedback physics from galaxies from the point of view of simulations. And unfortunately, galaxy formation is a very difficult problem, primarily because it's multi-scale, meaning it has an enormous range, spatial dynamic range. I like to illustrate that just by zooming in, right? So starting from the large scale structures of the universe on gigaparsec scales down to halo scales, say megaparsec, where dark matter halos and circumgalactic media are forming, down to individual galaxy scales, say on kiloparsec levels, but down further to parsec and indeed microparsec and milliparsec scales, where, say, the accretion disk around a supermassive black hole is launching a jet or a wind. Now, the problem here is that this is not just a problem of collapse. Unfortunately, what happens on these very small scales actually back propagates up to larger and larger scales. We know that feedback physics, say, on the scales of the accretion disk of the black hole can actually impact the baryons, and not only the baryons, also the dark matter distribution, say, on enormously larger scales. This is a 10 to the 12 orders of magnitude across these two scales here. In the best simulations, cosmological simulations which exist to date capture more like 10 to the 6 orders of magnitude. So we're still about 1 million times short in terms of directly resolving these processes. This is why understanding outflows in the context of galaxies is, of course, a challenging problem. And that leads us to the issue of how do we actually create these outflows via feedback processes, which is to say, how do we develop these kinds of models in simulations? Now, the question here is, how do we produce a model for galaxy formation, for feedback, and for outflows, which has some physically predictive power given these numerical limitations? Let me just make 3 brief claims here. So the first is that direct numerical simulations, or DNS, is impossible for the problem of galaxy formation, and it will always be impossible. That's simply saying that there are unresolved physical scales, and there will always be such. So what do? We need to develop approximations. So approximate models or subgrid scale models, which tell us approximately what is going on below the resolution limit of numerical simulations. And this is, of course, what we mean by subgrid physics. Now, I and many of my colleagues think that it's critically important to address this boundary, to identify it and to develop models which specifically address the problem rather than ignoring it, as is often the case in numerical studies, for instance, of diffusion, of magnetic field amplification on small scales, or turbulent energy dissipation due to a cascade to small scales, for instance. And of course, it's ideally nice if this scale separation between the resolved scales and the unresolved scales occurs at some physically convenient or meaningful boundary. In current cosmological simulations, for instance, resolving or not to giant molecular clouds is such a boundary. So outflows are a computationally difficult problem to tackle. And this means obviously that a number of different approaches have been developed to do so across a number of scales. We've heard a lot in the first few weeks about cloud scale simulations, so wind tunnel cloud crushing works. Next, of course, moving up in scale, we have patches, pieces of the ISM of disks, often in the form of these tall box simulations like Silk and Tigris. Of course, these citations are not by any means exhaustive here. I'm just giving a few canonical examples or recent examples. Next, of course, we have global idealized disk simulations. So now we have a global galaxy disk, which is, of course, critically important for resolving the evolution of outflows in, say, a fountain structure, but idealized. And here we're often talking about studying the impact of supernovae, so setting off bombs in this disk and seeing the kind of outflows that propagate away. Next, of course, we have idealized global halos. So in such a simulation, we might not even have a disk or care about the galaxy in the center, but rather a ball of hot gas and hydrostatic equilibrium with an NFW potential, say. Here, often the focus is on the black holes, studying black hole physics, feedback physics, and jets, and again, understanding how outflows are then generated and how they propagate away from the center of these halos. Next, of course, we have cosmological zoom simulations. So this is the first instance where the initial conditions are cosmological, by which I mean motivated by kind of lambda CDM constraints. And in practice, what this means is that the situation becomes much more complex, right? Particularly in the inflows and the lack of symmetries, which are present in some of the simpler approaches. Finally, of course, we're moving from individual zoom simulations of individual galaxies and halos to full cosmological volumes, where we are sacrificing more, even the resolution we have, in order to gain this kind of global perspective on the galaxy population as a whole. And I think you agree from left to right here, there's a different scales being resolved and different scales being probed in each of these approaches, all the way from the parsec and subparsec scales of interfaces and clouds to halo scales in the middle and cosmological scales on the right. And I admit, so in the next 20-25 minutes of this talk, I'm actually going to focus almost exclusively on cosmological simulations. Right? This is what I've worked on, and this is primarily where we can make this population-wide connection between the properties of galactic outflows and the properties of the galaxies themselves. So let's talk about supernovae and black holes in galaxy simulations. First thing we know, I think very clearly, is that stars release energy, and actually quite a bit of energy. So this is a classic plot from Agritz, 2012, showing essentially the energy injection rate for a stellar population as a function of time. The white line shows the bolometric radiation, the blue line stellar winds, and the red line type 2 supernovae after some appropriate delay time. 1As, of course, are not shown here. The issue is we have all this energy, but what do we do with it in the simulation? And the unfortunate answer is that what we do with it makes a big difference. So that's what I'm showing you here from this comparison study by Rosedahl. This is 6 different simulations of an idealized isolated galaxy disk with 6 different implementations of what you do with the energy available from stars. So no feedback, you dump it in as thermal energy, you dump it in a more stochastic sense, a delayed cooling model, you give a kinetic energy input, or a hybrid mechanical type model. And the point is that all 6 of these have been used and are indeed, they are used in galaxy simulations, different simulation projects. And as you can see by eye, the structure of the disk here, so face on and edge on, depends a lot on the numerical implementation of the supernova feedback. So a very similar study from Matthew Smith in 2018 showed that the outflow properties are also similarly affected. So on the top row is the outflow rate, and on the bottom row is the outflow velocity as a function of time. The left panel shows 1 kiloparsec above the disk, and the right panel 10 kiloparsecs above the disk. And again, the 7 colored lines here are 7 different models for how you do supernova feedback. And the point is simply that the outflow rates and the outflow velocities from such disks can vary by factors of many when you change how you input stellar energy in a type of galaxy simulation like this. Okay, so that's stars. We also know that supermassive black holes release energy, and indeed a lot of it. The typical argument goes that the mass density of black holes is something like 0.1% that of stars in the universe, and yet the energy available from black holes is roughly 10%, a radiative efficiency of 10% times the MC squared, and compared to the usual argument for supernovae of roughly 10 to 51 ergs per 100 solar masses formed. If you take the ratio of these two, you actually find that it's almost unity, which means that the total feedback energy available from black holes is somehow comparable to that from supernovae across the universe, and so you better not neglect it. Now, of course, very detailed small-scale simulations of black hole accretion disks are starting to probe the physics of how this energy is actually released from the accretion disk and from the emergence of relativistic jets, say. And to be honest, we have not yet coupled very closely galaxy scale simulations to these kinds of small scale black hole simulations. I want to give you one example of how we're starting to do that, though. So this plot shows you the radiative efficiency of a black hole as a function of its spin. And this is an answer obtained from small-scale simulations of McKinney and as implemented in the new New Horizon simulations, which are cosmological galaxy formation simulations. So the point here is that if we can measure or think that we can track the black hole spin evolution in the simulation, we can actually use this answer from the smaller scale simulations to tell us what the radiative efficiency should be. And again, the radiative efficiency is this not free parameter, but is this parameter sitting in between m dot c squared, the rest mass secreted energy, and the amount of feedback energy we have available to use in our galaxy simulation to drive outflows. Okay, but if you're not doing GRR-MHD, which means general relativistic radiative magneto-hydrodynamical simulations of accretion disks around supermassive black holes, and I think we're on the same page here, not many of us here are doing that, then what you're doing in practice with this energy is very simple, right? We're actually developing very simple models, subgrid models, for how this energy released from supermassive black holes can couple to the galaxy and thus drive outflows. And what I like to do actually is give a very practical sense of how we implement supermassive black hole energy injection in galaxy scale simulation. So this is a kind of schematic diagram of a CGM, of a halo out to the virial radius, and you should imagine that there's a black hole sitting in the very center. So you accrete some mass, you have some available energy. What would you like to do with it? You could dump it in as thermal energy in the local vicinity of the black hole, for instance. You could inflate a thermal bubble offset out in the ICM, out in the halo. Perhaps this is mimicking an unresolved relativistic jet, which goes out and inflates such a bubble. You can create large, big, energetic bubbles, or maybe you create a population of smaller, smoother, gentler in time thermal energy injections, or maybe you do something completely different. Maybe you inject momentum, so kinetic energy. Maybe you do that locally and give it a particular direction. Maybe you do this in a bipolar sense, or maybe you make an isotropic energy injection. Maybe you do none of those things. Maybe you simply capture what you think the black holes actually do, right, which is to offset the cooling flow. So maybe you simply shut off the cooling by hand, so to speak, in the halo gas. Now, what's interesting, I think, is that actually all of these different methods are used by different simulations in different contexts, and they're actually all used in practice, subject, again, to additional detail. So, for instance, if you're dumping in thermal energy, is it continuous in time or is it bursty? And some simulations do both. Does one of these modes act at all accretion rates all the time, or is one only in the high accretion state or low accretion state of the black hole? And again, you have different simulations implementing different assumptions and different model choices in this regard. So now that I've scared you enough, I think, as to how we actually implement feedback in galaxy scale simulations, I want to jump right into the question of what kind of outflows are produced in these simulations. So there's an overarching theme to the next second half of this talk, and that is as follows. Despite the simplicity, which I've just shown you, right, the simplicity of the subgrid models for feedback, which is simplicity at the scale of the energy injection, which is the resolution scale, the very small scale of the simulation, the resulting flows which develop and propagate away from galaxies and through the CGM are quite interesting, and they display a number of complex and almost emergent behaviors and properties which are somewhat unexpected. So I'll start with point number one, something I think very not controversial whatsoever, at least I hope. Bigger galaxies have faster outflows. I'm showing you a scaling of outflow velocity as a function of galaxy stellar mass. So this is from the TNG simulations at redshift 2. The blue points are showing you the 75th percentile of velocity, and the orange, the 95th percentile. So very roughly speaking, outflows, when you're thinking about 10 kiloparsecs away from the galaxy, have speeds of order 100, 200 kilometers a second for low mass galaxies, increasing up to, say, 400, 800 kilometers a second at the Milky Way mass regime. If we actually look at the distribution of outflow velocities around galaxies of different masses, it's quite interesting. So this is showing you the amount of mass flowing as a function of velocity. Each line shows the stacked average for galaxies at different stellar masses, increasing from 10 to the 8 for small galaxies up to 10 to the 11.5 in pink. Now what we see is that around small galaxies, velocities of outflows are relatively small, right? Few hundred kilometers a second. They kind of take the shape of this compact core, which gradually grows to higher and higher velocities. And this, again, this is low mass galaxies. This is where supernova type 2 are driving the energetics and the production of these flows. And they result in these mild, I would call them outflow velocities. Until we get to some critical stellar mass, galaxy mass, which here is about 10 to the 10.5 stellar mass. This is where, in this model, black holes start to act. It's where they really start to have an influence on driving outflows away from galaxies. And what the black hole feedback does in superposition to the supernova feedback is it produces these very high velocity tails. So the black hole feedback is what results in these simulations in outflow velocities which exceed 1,000 kilometers a second, out to many thousands of kilometers per second. Now, if these numbers startle you a bit, I put here the average outflow speed for a Milky Way mass galaxy at redshift 0. So the median, and it's something like 150 kilometers a second, so relatively mild. That's point number one. Point number two, which I think is quite important to point out. The properties of outflowing gas in these kinds of galaxy and cosmological simulations are distinct from what you put in, which is to say what you get out is not what you put in. I think that's very clearly seen here on this plot on the right. So this white line for low mass galaxies actually shows you a model assumption in these TNG simulations, which is a minimum wind velocity of 350 kilometers per second. Now what this is mimicking is unresolved physics for low mass galaxies. But when we go and actually look at the flows which emerge from these systems at any resolvable scale, we see that they actually move at lower velocities than this supposed minimum, which means that the properties of the outflows, when you see them propagating through the halo, have decoupled from the assumptions from the model inputs at the resolution scale, which I also call the scale of energy injection. And we'll see that theme come back. Okay, so point number three. This may be either extremely obvious to you or extremely controversial, and I'm quite curious which. So point number three is that outflows slow down with distance away from a galaxy. They do not speed up. Again, I'm showing you that here, outflow velocity is a function of galaxy stellar mass. This is the median relation when you're considering flows at different distances. So red, blue, green are 10, 20, and 40 kiloparsecs away from that galaxy, and you can see that the velocity drops by roughly 50%, or a factor of 2. Now, if I compare that to the escape, say the delta escape velocity to go from 10 kiloparsecs to the virial radius, so you'd have to be on this line to move from 10 kiloparsecs out to the edge of the halo if gravity was the only thing holding us back. And we can see, for instance, that this red line at 10 kiloparsecs is above this point, which means that this is showing the 90th velocity percentile. So a high velocity tail of gas can have sufficient velocity to escape this system, which is of course not true if we look at the 50th percentile, so the bulk of the flow, which is at much lower velocities. But still, you see as you move out, red, blue, and green, increasing distances, the velocities slow down as you move away from the galaxy. I want to show you a perspective of this from the Eagle simulation. So this is analysis from Mitchell, 2020. This is even more direct. So it's outflow velocity as a function of distance away from the galaxy, normalized by the real radius. The solid line shows all gas, which is sitting there in space, and the dashed line, which you should focus on, actually shows the gas which has left the ISM, which has been ejected from the galaxy. And the outflow velocity is a monotonically decreasing function of distance everywhere in the resolved halo, in the resolved flow. I think the point here is that winds propagate into something, right? They propagate into the CGM, into the pre-existing CGM, and not a vacuum. And I think to capture the proper evolution of winds, we should think more about this difference between simulations which capture the mass and the properties of the medium into which outflows propagate, as opposed to models which model propagation into effectively a vacuum. In the context of the Eagle simulations here, the interpretation of this declining speed with distance is a general conversion, right, from kinetic to thermal supports for the wind. Point number 4 is that winds are not isotropic. And so I show this image again. It's one of my favorites. It's showing you the geometry of a flow emerging from a disk galaxy. So the color in the background is the gas density map, and more importantly are the streamlines on top, which show the velocity field of the outflow and the inflow for that matter. And this is a disk galaxy. I've oriented it edge on, which means it's in the horizontal orientation, if you like. And what you see is that outflows, as indicated by the arrows, are preferentially propagating along the minor axis of this galaxy, whereas inflows tend to be found along the other directions, more aligned with the major axis of galaxies. We can see this more quantitatively by looking at the amount of gas outflow as a function of angle. So from pi to minus pi, which is going around a circle from 0 to 360 degrees, for the minor axis of the galaxies I've indicated at these 2 points. And so where you see yellow, that's where the mass outflow rate is the highest. And you see how outflows are not isotropic. They're not equally spread in angle, but rather preferentially are propagating aligned with the minor axis of galaxies. Why this is particularly cool in the context of simulations is that when we inject energy from supernovae, so this is a 10 to the 10 stellar mass regime I'm thinking about. This is where supernovae are doing the work. When we inject energy, it is completely isotropic at the injection scale, which means there is no preferred direction whatsoever on the scale of 100 parsecs or so. This is the scale of the energy injection in this simulation. However, when we go and look at the resolved flow which emerges from the galaxy, you see it picks up this natural collimation, in effect, an unavoidable consequence, right, of having the disk in one direction and having the pressure gradient, the path of least resistance, in the other direction. But this is a very nice example of what you get out is not what you put in, and how simplified models for subgrid physics can lead to more interesting behavior on resolved scales. Another interesting point is that this collimation requires the disk to be here, right? If there was no gaseous disk impeding the flow in the major axis direction, it would be an isotropic flow. And indeed, at high redshift, galaxies are not disks. So we actually have a very clear expectation from the simulation, which is that only as you go to lower and lower redshift, as galaxy disks form in the universe, which is to say the gas settles into rotationally supported thin structures, that is when we expect such a collimation to emerge. Very obviously by redshift 1, but in this simulation, it's very hard to find such a signal at redshift 2 or higher. Okay, point number 5 essentially is that black holes make very cool outflows. It's just my excuse to show the interesting structure, morphology, and properties of what is a supermassive black hole driven flow in these TNG simulations. So these 5 rows show time evolution. Each is about 100 mega years apart. And in the very initial phase here, what you're seeing is the first onset of strong black hole activity in this galaxy. This is the onset of quenching, because this black hole activity will eventually push this galaxy off the main sequence and quench its star formation rate. The left panel is showing you velocity and the right panel temperature, where you can actually see already in this first image, you look at very small scales, you see kind of 1, 2, 3, 4, 5 or so loops of high temperature gas. These are 5 discrete energy injection events from the black hole, which have already taken place and are now propagating outwards. You see what this flow evolves into is a very high velocity, so exceeding 1,000 kilometers a second flow as it passes the virial radius of the halo, which is indicated by the white circle, so on very large scales. This is a very high temperature flow, so it's almost a high pressure, high temperature bubbles which are being inflated by the action of the supermassive black hole, which then expand into the CGM and out into the intergalactic medium. I want to point out here that if I zoom in, so the galaxy in this image is minuscule. The galaxy, I've oriented it edge on again, but in the vertical direction. So it looks something like this if I zoom into the center. And the region of influence of the black hole is this little white circle here. And that's the region where energy is injected, leading to these large-scale outflows again. I want to point out two kind of cool features here. So the first is this guy. You see it. This is a satellite galaxy, which runs through the middle of this halo and gets destroyed. All right, so what you see at the final time is this population of cool, high-velocity gas clouds moving outwards, which might be mistaken for cold gas entrained or ejected in a black hole-driven wind, right? But in reality, this is simply stripped interstellar medium gas of a satellite galaxy. The other cool thing, if you can see, a very small here, so Pratik and I were particularly intrigued by this. These are cold clouds that look to be raining down onto the galaxy in the orthogonal direction to the outflow, so along the major axis here. You can actually see a bit more structure in the zoom in, right? So this seems to be a bit of a condensation or precipitation type process. Remains TBD what exactly is going on here, but it seems to be a signature of fueling, again, in a volume of the halo distinct from the outflow. Let me add on two additional panels here of the same outflows, so density and metallicity. In density, you can clearly see the morphology of this flow is a pile-up of gas in almost a shell, right? So this succession of outflows have driven shells of overdense gas, which leads to this underdense expanding bubble feature, which is also dredging up very enriched metal, right? So before this black hole really gets started, the intergalactic medium, which you can see right on the outskirts here, is sitting down at 0.1 solar or less, actually. But after a few hundred mega years, this black hole-driven outflow has actually taken supersolar gas from the galaxy itself on very small scales, polluted the entire circumgalactic medium, and indeed the near-field IGM as well. Point number 6 is that these black hole-driven outflows also produce in these TNG simulations a multi-phase structure in the outflows, which I think is quite interesting. So similar to before, what I'm showing you here is the distribution of outflowing mass in terms of its temperature. And each line shows the stack for galaxies of different masses, from 10 to the 8 all the way up to 10 to the 11.5. Now the main component you see is this, I call it hot phase. So it's this large Gaussian kind of distribution, where the peak is shifting to higher and higher temperatures, basically tracking the virial temperature of these increasingly massive galaxies, right? Until we get to the purple line here. Again, this is 10 to the 10.5. This is where black holes start to do their work. And at this point, we actually see the emergence of this secondary peak. So the emergence of a bimodality in the temperature distribution between a colder component and a warmer component. This is a signature of the direct ejective nature of the black hole feedback, literally throwing out cold gas from the central galaxy at quite high intermediate velocities out to very large distances away from galaxies. It's also important to point out that these phases at different temperatures have different kinematics. So that's what I'm showing you here. This plot shows the plane of velocity, outflow velocity, and gas temperature, where again, yellow and green indicate where the mass flux is. And so what you see is that the colder component, 10 to the 4, 10 to the 5 Kelvin, has moderate velocities, a few hundred kilometers per second, and the bulk of the hot component does as well. However, this tail towards extremely high velocities is contributed only by the hot component. So the different phases have distinct kinematics. And I think another important point here to mention, you can see it clearly on the left panel again, is that the colder peak is much smaller than the hotter peak. Right? This is saying that actually the mass flux at these distances for these kinds of massive galaxies is dominated by the hot phase, which unfortunately is of course very hard to observationally characterize beyond the local universe. So if these kinds of expectations are true from the simulation, it means that it's going to be very hard to find the bulk of the outflowing mass if it's in such 10 to the 6 to 10 to the 7 Kelvin phases. Now this link between kinematics and phase is very generic. So here I'm showing you a plot from M. Schneider's recent paper. I've flipped it, I've inverted it, flipped it horizontally so that the axes are actually the same, very similar to the plot on the right. So increasing temperature and increasing outflow velocity, and you see this exact same banana shape, again showing you that the hot tail that the high velocity tail is coming from the hotter component, whereas the colder component of the outflow is at more reasonable velocities. Okay, point number 7, mass loading. So I managed to get 75% of the way through this talk without ever mentioning mass loading, which is a bit strange for an outflow talk. The definition, of course, to get us on the same page, is the mass outflow rate normalized by the star formation rate of the galaxy itself. So let me show you the relation of mass loading of outflows as a function of galaxy stellar mass. This is again from the TNG simulations. I focus on the blue line. So mass loading factors are high for low mass galaxies, and then they drop from, say, 10 many tens, 50, maybe even 100 for very small dwarfs, down to a few. Mass loadings of a few for the Milky Way mass regime. But at this point, you see that something rather strange happens. This relation actually has an inversion, and the mass loading starts to go up again. And this is because, again, at this mass scale, black holes start to dominate the energetics of outflow production. It's no longer the supernovae doing the work, but instead the black holes, which drive very strong outflows. And at the same time, so they're pumping up the outflow rate, but at the same time, quenching the systems and depressing the star formation rate, which leads to this very pronounced feature. This is also seen in the Eagle simulation, which I find very interesting. So this is complementary similar analysis from Peter Mitchell's recent paper. The TNG simulations are shown in blue, very similar to the lines on the right, on the left, and the Eagle simulations are shown in yellow, where in general they find slightly lower mass loading factors at the same galaxy masses on the main sequence here, but also this inversion, which in the Eagle simulation is also due to the startup of strong black hole feedback, again at this mass scale, 10 to the 10 to 10 to the 10.5. Now, what I think is very interesting here is that this feature in Eagle is only seen in 2 out of 4 of these yellow lines. If you notice, it's only seen at the large distances, 50 kpc and the virial radius. And in contrast, near the galaxy, the mass outflow rates are very small, 10 and 20 kiloparsecs. This is actually completely opposite to the behavior seen in the TNG simulations, where you see the mass loading factors are large at 10 kpc, and then they start to drop to larger distances. So the relation is actually the complete opposite with respect to distance. This is a signpost that in these 2 simulations with these 2 models, the propagation of winds through the CGM is very different. In TNG, they are declining, they're getting weaker and weaker, whereas in Eagle, they're actually getting more and more mass loaded, and more mass flows out across the virial radius than across the galaxy itself. The implication here is that there should be very different fountain flows, right? Very different recycling properties in these halos in these 2 different models. Let me slide those over to the left to give a broader perspective. Again, the mass loading factors. So on the top panel here, I'm showing Fire simulation, and on the bottom, Nihao. And the pictures are very similar. So in Fire, you have very large mass loadings, right, for dwarf galaxies, dropping to of order unity around the Milky Way mass scale. And similar in the Nihao simulations, mass loadings of order 100, dropping down to unity around the Milky Way mass scale. I particularly like this figure at the bottom because the blue open symbols actually show the mass loading factors, which would be inferred if you only considered very cold gas, so less than 10 to the 3 Kelvin, which would be observable as, say, a molecular phase, which makes it very clear that the inferred mass loading factors depend sensitively on the phase which you're observing in order to make this estimate. Okay, so general trends versus stellar mass, I think, is a very common feature. Large mass loadings declining to of order unity or a few at the Milky Way, so 10 to the 10.5 stellar mass. I think it's quite important to point out, only on the left here do we see this feature of the inversion of the mass loading, because this is due to black hole feedback, which is not present in the Fire simulations or the Nihao simulations, for instance. As a function of radius, it depends very strongly on the model. So in some cases, mass loading factors can decline with radius, as is the case in TNG or Fire, but in other cases, they can actually increase with radius, and this should again be reflected in the global gas content in the baryonic closure of these halos, how much gas is left, and should be, I think, observationally constrainable in that sense. Versus redshift is a similar issue. Some models show slightly increasing mass loadings, others slightly decreasing as redshift goes to 0 at fixed mass. So it really depends. And the comment on redshift lets me show, or gives me an excuse to show one more plot from a different simulation. This is from the Horizon AGN simulation. So no longer mass loading factor, but actually raw mass outflow rate, solar masses per year, as a function of galaxy stellar mass. So these outflow rates are actually a bit smaller, a bit weaker than in most of the other simulations I've showed you. But when you don't do the normalization, we can get a more clear sense, right? Big galaxies drive very strong outflows with enormous outflow rates. And as you go from low redshift up to high redshift galaxies drive enormously strong outflows, just so we don't lose track of that fact. High redshift galaxies also drive very fast outflows. So this is again outflow velocity versus galaxy mass in the TNG model, going from redshift 6 down to redshift 0. And at fixed mass, at high redshift, outflows can be a factor of 2 or factor of 3 faster. This is the outcome of this model in particular. Okay, point 10 is a very brief one. Back to the mass loading factor and this feature of the inversion. So the definition of mass loading has a normalization of the star formation rate, which is in essence an implicit assumption that the energetics involved in creating this outflow come from supernova type 2. And I think we can see regimes where this is not true and where this assumption, or rather this normalization, can lead to very biased conclusions. That leads me to make a very provocative X here to cross this out and to say, let's not do that. Let's instead stick to the simpler, more direct measurement of the outflow rate itself. I think, okay, I'll say this briefly. I think despite having crossed out the star formation rate in the mass loading factor, let me point out that outflow properties do, of course, relate in some cases directly to the star formation properties of a galaxy. So let me walk you through this figure very briefly. This shows you galaxies on the plane of star formation main sequence offset versus mass. So by star formation main sequence offset, I mean distance from the main sequence. So the main sequence is here, sitting at 0, and points up here have higher star formation rates, and points down here have lower star formation rates. The color shows how fast velocities are emerging from those galaxies relative to the average. So red means that galaxies drive faster outflows than the average galaxy at that mass. Blue means galaxies drive slower outflows. What we see is a clear correlation, right? Outflow velocity correlates with offset from the star forming main sequence, correlates with star formation rate. In particular, if you're above the star formation main sequence, you are driving faster outflows in this model. But as we saw before, at high mass, this actually inverts this relation. So for massive systems, these red pixels down here show you that it's actually low star formation rate galaxies which start to drive the fastest outflows. So this inversion of the relationship between outflow velocity and star formation rate properties is another example of the complication introduced when you also are considering the role of black hole feedback. Okay, this is my rant on comparing simulations to observations, which is to simply say we need to work more on these comparisons because I don't think we're doing good enough so far. And I want to end on a slightly more positive note, which is, does the fact that we saw how inflows and outflows occupy different volumes of the halo, is this imprinting any sort of signature which we can observe in the CGM properties? So this was a study led by Salim Peru, and the idea was that if we look at the metallicity of CGM gas as a function of angle with respect to the galaxy, we should see a preferential signal of enhanced metal along the minor axis of galaxies, right, due to the preference for outflows to occupy this space as opposed to metal pore inflows to occupy the major axis aligned directions. And indeed, if we go to the simulations, that's exactly what we find. So a clear prediction for a correlation between gas metallicity and the azimuthal angle between a galaxy and an absorber, say at 100 kiloparsecs, where you have lower metallicities along the major axis and higher metallicities along the minor axis. Something which is Not yet been observed yet, but hopefully will be in the future. Okay, so instead of concluding anything, I simply labeled the conclusion slide points to argue over. The first, the mass outflow rates and the mass loading factors, especially of the low mass galaxies. These are very high in the simulations. These are traditionally very low in the data. Are we measuring these things accurately, observationally? Are we comparing these things correctly between the simulations and the data? The mass loading factor itself is a very supernova-centric perspective, which breaks down in very important regimes, and these important regimes can include, I would claim, the Milky Way halo mass 10 to the 12 itself. Outflow driving feedback does not mean supernovae. There are other physics at play, and indeed, the energetics of the supermassive black holes change the entire outflow galaxy connection. What you put in is not what you get out. You have these signatures, for instance, in the collimation and in the divergence of wind and outflow properties as they are hydrodynamically evolved through the halo, basically, which leads to many complex behaviors in these kinds of cosmological simulations. And finally, that the angular variation, which I think is something we should think about more, angular variation of circumgalactic medium properties have the ability to nicely probe many aspects of outflows. So end just by flashing again these two very high dimensional functions, so to speak, and to propose that we work and think about how to measure quantitatively how much gas is moving as a function of all these physical properties and these galaxy properties, both in simulations and empirically. And thank you very much.
Thank you very much, Dylan. Excellent, excellent presentation. Really covered a lot of ground there and a lot of discussion in the Slack channel to follow up for our panel. I will give everyone, let's recommence. It's 9:02 now. How about we take an 8-minute break to allow everyone to get a drink of water, use the bathroom, and check over the Slack and go through the comments. There's a lot of discussion there. I will draw from that for the discussion panel, and so people can add to it, or thumbs up things that they think are relevant comments, or thumbs down ones. Drummond had a thumbs down during the talk, so controversial points, but this is great for discussion. So we'll see everybody in about 7-8 minutes. And again, thanks, Dylan. Excellent talk.
Thank you.